Welcome to the 15th chapter on winning strategies and regions in the logical foundations of cyber-physical systems textbook. We will, in this chapter, develop and identify a simple denotational semantics for hybrid games based on their winning regions. That is, the set of all the states for which there is a winning strategy that wins the game for all strategies that the opponent might possibly choose. This denotational semantics continues the successful trend that this entire textbook followed of understanding all the operators in a compositional way, that is, where the meaning of a composed hybrid game is a simple function of the meaning of the pieces, as was already the case and crucially exploited for hybrid systems. For repetitions in hybrid games, such a semantics will turn out to be shockingly subtle. That is, uncovering a surprisingly rich complexity in hybrid games that is quite different in characteristic nature than it was for hybrid systems. And that's the first indication why hybrid games come with their own unique set of challenges beyond what hybrid systems already had in store for us. Wait a minute. Why do we need semantics for hybrid games? Didn't we already have one from the previous chapter when we were drawing these game trees? Well, yes and no. Of course, the operational semantics that we have seen, where you unfold the tree of actions in the game and then worry about who gets to choose what under what circumstance, that, of course, gives us a lot of intuition in terms of how gameplay works out. And that's a useful intuition for us to work with going forward, but the challenge is making that mathematically rigorously precise. Just remember how difficult it was to say things like, well, you keep on repeating and just don't decide to say go, 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 go all the time, because, well, never-ending gameplay totally ruins determinacy, so the property that one player always has a winning strategy, because there simply is never a state in which the winner is even declared. And the study of an operational semantics for hybrid games can be made completely rigorous. But that would lead us down a path of descriptive set theory, which is exciting in its own right, but also rather difficult. In comparison, we will now discover a denotational semantics, with the difference being that a denotational semantics, just like in the rest of the textbook, studies the mathematical object that a syntactic expression denotes. What we're going to learn today in the modeling and control side is to understand the core principles of adversarial dynamics that is resulting whenever you have multiple agents with possibly or really conflicting actions. That, of course, come to think of it, plays a role in many CPS applications. In particular, we will look at interesting nuances in their precise semantics, which is shockingly subtle, especially for the case of adversarial repetitions. That doesn't make it less important. On the contrary, that makes it more important to understand these correctly. And as a byproduct of this development, we'll also have an opportunity to look into the role that fixed points play here as a very naturally motivated example. On the computational thinking side, we will be leveraging fundamental principles from computational thinking in programming languages to devise a logical extension. So we will extend the language we've already seen of differential Lemma logic and hybrid systems all the way to differential game logic and hybrid games by, well, first of all, extending the syntax, done that, add the duality operator, but also extend the semantics of these program models and the specification and the verification logics with this operator of duality that incorporates adversariality of the system in a very modular way into the hybrid systems models. That way will enable us to also reflect on an interesting difference that is also valuable for hybrid systems, namely the difference between a denotational semantics, where we focus on the mathematical object to which a syntactic expression refers, compared to an operational semantics, like the game trees we've seen, where the actions that happen successively as the game unfolds are in our focus. On the CPS skills side, we will look at understanding a semantics of CPS models that involve in adversarial dynamics. And that's, of course, important whenever you need to understand how a state evolves over time as multiple agents react to one another. These multi-agent operational effects are very important, especially because they do involve mutual reactions. Just think of it. If you're controlling a robot and I'm controlling a robot and the two robots meet each other, then what my robot does will be a reaction to what your robot just did, and what your robot will do will be a reaction to what my robot just did, but that depends on what your robot just did, and so on, vice versa. How does this ever stop? Or what exactly does it mean? How can we understand the behavior of these multi-agent cyber-physical systems, and how we can reason our way through this to make sure that as you are designing your own robot, for example, you make sure your robot does exactly the things you want him to do, no matter what my robot is interfering with it. What we've seen last time already is a syntactic development of differential game logic. And we've taken a pass through a number of interesting modeling exercises so that we really truly understand the fundamental role that hybrid games play, but we haven't been very precise about their semantics yet. What we've seen in the syntactic category of hybrid games is that they do involve discrete assignments, test games where we're testing a logical formula Q to check whether it's true, and if Angel fails this challenge that Q is true, she loses the game prematurely, basically because she fouled up and violated the rules of the game. In a differential equation, Angel reaches an important decision to follow a differential equation x prime equals f of x that we wrote down here, but for her favorite amount of time. So some real number duration greater or equal 0, but the obligation on her end is to make sure that she can't possibly ever choose a duration unless it is true at every point in time along the solution of this differential equation x prime equals f of x that the state of the system was within the region Q, which again is a logical formula. The game of choice between alpha and beta gives Angel player the opportunity to choose whether she would like to play the alpha subgame or whether she would like to play the beta subgame instead. Think of it like controlling a robot and giving the robot the opportunity to exit the building or to remain within the building trying to find a charging station. Depending on the objectives that the robot has, either the left or the right action will be the better one, and depends on the purpose of what has happened so far and what will happen next, which one is clever, in case the alpha choice beta is embedded in a bigger hybrid game. The sequential game first plays the game alpha, and whenever we're done with that, and no player has lost yet due to prematurely violating the rules of the game, then the game continues with beta. In the repetition game, alpha star, Angel gets to decide how much she wants to repeat this. And in fact, she gets to decide by inspecting the state and says, yep, I don't like the state yet. Let me do that alpha game once again. And then she again inspects the state and decides whether she wants to stop or go again. Any number of times. Duality, well, that's now the most important operator because a game needs two players. But so far, everything I said was talking about Angel's choices and Angel's choices and Angel's choices in the duration, in the game of choice between left and right, in the repetition game, and that would make her internal opponent, a demon, sit around being rather bored. He comes in at the duality operator. The dual game, alpha dual, is what you think it is. It's the duality of the alpha game, where every choice that the Angel player used to have in alpha Now it's demon's choice. And every choice that the demon player used to have in alpha is now angel's choice in alpha dual. So think of alpha duality as what happens when you turn a chessboard around by 180 degrees so that all of a sudden you're playing the choices that your opponent used to face a moment ago. And by nesting the duality operator with the others, we saw last time already how that can define also choices for the demon player, repetitions for the demon player, tests and challenges for the demon player, or differential equations that are under demon's control. The hybrid games, strictly speaking, only describe the game form, sort of the rules of the game, but they don't define a purpose yet. The purpose comes in the differential game logic formulas, which start out like logic does, for example, with arithmetic comparisons of E and E tilde terms, logical negation, conjunction, quantifiers for all or exists of the reals, and most importantly, that modality operator where for every hybrid game alpha that's recursively built like so, and for every differential game logic formula P that's recursively built like so, does alpha diamond P express that player angel has a winning strategy in the hybrid game alpha to reach one of the states in which the differential game logic formula P is true, whereas alpha box P expresses that demon has a winning strategy in the hybrid game alpha to reach one of the states in which the differential game logic formula P is true. So remember, the P declares the objectives of the player who actually wins. Well, players could still lose prematurely in case they violate the rules of the game, for example, failing test or challenge games or evolution domain constraints in the middle of playing the hybrid game. But the actual winning really only takes place afterwards. Remember also, the mnemonic to tell them apart is that angel has wings. So that's her winning strategy operator, and that's demon's winning strategy operator. Now let's develop a semantics, but let's not go down the path of the operational semantics anymore that the previous chapter did. But let's develop and continue the successful trend in this textbook of understanding things in a compositional fashion using the denotational semantics. For formulas, well, that's mostly easy because formulas in differential dynamic logic already used to have a compositional semantics, and, well, come to think of it, it's not like we should change the meaning of conjunction and logical negation just because we're all of a sudden talking in the context of hybrid games. So, still, the meaning of a formula will be a function that maps the formula to the set of all states in which it happens to be true. As usual, the meaning of E1 greater or equal E2 is the set of all states in which the value of the left-hand side term is greater or equal the value of the right-hand side term. So evaluate the left-hand side, evaluate the right-hand side. And if the left-hand side indeed is greater or equal, of course the formula is true in that state. Logical negation. The set of all states in which not P is true is the complement of the set of all states in which P is true. So remember that we can also write this as the set of all states subtracted the set of all states in which the formula P itself is true. That's the complement. The set of all states in which P and Q is true is still the set of all states in which P is true, intersected with the set of all states in which Q is true. So over here, both P and Q have to be true, which is precisely what the logical formula P and Q says in logic. But now it gets a bit more complicated. So what's the meaning of alpha diamond P? What's the set of all states in which it is indeed true that angel has a winning strategy in the hybrid game alpha to reach one of the states in which the differential game logic formula P is true? Well, we do know the set of all states in which P is true, but it's not clear whether we can define the set of all states in playing the hybrid game alpha in which we're in the winning condition, which is the set of all states in which P is true. if we can define this, we can call it sigma alpha. That's easy, but how do we define it? It's not clear that we can define it in the same way that we used to define it for a hybrid program. So remember, we used to define it like so. We gathered the set of all states omega such that for some new state nu is the postcondition true. For a new state, I can reach from the old state omega by running the hybrid program alpha. Well, that definition just doesn't exactly work for hybrid games. And why is that? Well, for one very obvious reason, because the runs are only defined for a hybrid system alpha, and we haven't defined that yet for a hybrid game alpha. So we would have to augment the definition to ever make that happen, but it's more subtle than that, because the point is, if we were to settle for a condition of this particular shape, then, well, for Angel to have a choice of winning, she would have to predict a new state nu that satisfies the winning condition P, and then she'll have to win into this one tiny little state, which is really hard, because all the daemon has to do is to make sure the gameplay ends in a state in which maybe Angel also would have won, but it's not the one new state nu that Angel predicted here. In other words, the reachability relation semantics that we had, or any other reachability relation semantics you could be writing down, it just isn't prepared for the interactive semantics of gameplay, because it's very important for the individual players to have the opportunity to interact with one another and change their minds and play with different strategies, and none of that is apparent just from reachability relation semantics. And of course, nobody ever said that alpha diamond P, like in differential dynamic logic, would still mean there is one way of running the hybrid game alpha to a state where P holds true. No, because the opponent might interfere. Alpha diamond P means there's a winning strategy for Angel to win into a state where P is true. Just like alpha box P no longer means, just like in hybrid systems, that all ways of running the hybrid program could take us to states where P holds true. No. The opponent might interfere, and it's okay if not all of those runs end up in P. What is important is that daemon has a winning strategy to strategically make it to one of the states in which he's won the game, no matter what the opponent is doing. So on both of those opportunities, it's very important to take into account what the opponent might do, and they're expressing properties of existence of winning strategies. Now, well, you could write down a semantics in which you make the winning strategies explicit, but then all of a sudden your semantics would have to say, well, do I have a function in which I map the state to the action that I'm doing, and do I have such a function no matter what function the opponent is following as a strategy? But that, again, would make us fall down the rabbit hole of operational semantics, which is possible and equivalent to what we're going to develop, but much more complicated. Instead, what we're going to do is augment the sketch of a semantics for differential game logic formulas with a definition of this function, sigma alpha, well, and delta alpha, that for a set of all states that's declaring the winning condition, so where would the player have won, this function will have the purpose of defining in one swoop the set of all states in which Angel does have a winning strategy to win in the hybrid game alpha to make it into this particular set of still states, whereas the delta alpha will define the winning region in which the daemon player in the hybrid game alpha has a winning strategy to make it into the set of still states. Let's define those two functions, sigma alpha and delta alpha. How could we define them? We're supposed to define them in the compositional fashion. We're not supposed to look into what the winning region looks like. It's just some set of states. But we can still define it as a function of what the hybrid game alpha was. In fact, we should probably be defining it in a compositional fashion, so as an inductive definition on what the shape of alpha is. Because that is the way not just how denotational semantics works, but also how we've been increasingly successful in hybrid systems already. So remember, we're not going for this because that's defined only for hybrid programs, not for hybrid games, and it doesn't do any good for interactive gameplay, which we're now after. Let's define the winning region in which Angel has a winning strategy in the game that merely consists out of the simplest game you could think of, the game of discrete assignment, that puts the value of term E into the variable x. Under what circumstance does Angel then have a winning strategy to make it into the set of all states x, which we don't know anything about, it's just some set of states. In pictures, if this is the set of all states, then from what set of states does Angel have a winning strategy to make it into there by following this assignment? Well, if the program, for example, does something like x is x plus 1, right, then we're basically asking from which set of states does Angel have a winning strategy to make it into this region by adding 1, which basically just means which set of states have a successor that's in the set of states. It's not like Angel actually has a whole lot of choices, any at all, when playing an assignment game. So in other words, the set of all states in which Angel does have a winning strategy to make it into x in the assignment game is just, well, the set of all states, such that when we take the state and replace the variable x with the new value it's going to get, so the value that the right-hand side expression of the assignment has in the state omega, if that new state over here, if that new state is in the region x, then it's precisely the set of all states in which Angel does have a winning strategy in the game of assignment to make it into x. We just jump over there, and then it gives us the winning region, so the set of all states in which Angel would win by an assignment to make it into x. That was actually very easy. Come to think of it, that wasn't very different than it was in hybrid systems, but that's of course also the point. A game that doesn't have any choices just yet, and in fact it doesn't have any different behavior at all, it just has one single deterministic unique behavior, that should basically have the same semantics and as a hybrid system as it would have as a hybrid game, even though we wrote them down a bit differently, no longer as a relation, but as a winning region. Now, what if it were a differential equation, though? What if we're defining the winning region in the game that consists of a differential equation, x prime equals f of x, or a system, within an evolution domain constraint Q. And we're asking ourselves, from what set of states does Angel have a winning strategy in this differential equations game to reach a state within the winning condition x? So if the winning condition x, we're asking ourselves, where does Angel have a winning strategy to make it into that by following the differential equation? Well, of course, I guess that should be the set of all states for which there is a solution of this differential equation, which after some period of time lands in x, and if it does, then Angel has a winning strategy, just follow that ODE, for that particular solution from this state, if, of course, we also make sure that this particular solution was not just a solution of the differential equation x prime equals f of x, but also observe the evolution domain constraint Q at every moment of time like this. Okay, let's define that in mathematics. The winning region for the differential equations case is the set of all states that a solution could start in, so pick any arbitrary solution of the differential equation and the evolution domain constraint, which starts at an initial state 0, then the set of all states that are like that is in this winning region whenever there is a solution and also a time r, the final time, such that at this final time, like way over there, we are in the winning condition x. So we've reached the goal after r time units. So whenever there is such a time and such a solution of the differential equation, then because it's Angel's choice, all she needs to do is just wait long enough precisely for our time units and say, now I stop, oops, I've won the game. Slight footnote, just to make our thoughts a little bit easier here, I'm suppressing the subtle nuances in terms of ignoring the values of the x prime variables, because we can easily define ourselves out of that, just like we used to do in parts 2 of the textbook. Now, the other atomic game we could be playing is a challenge game, a game where we're testing whether the logical formula Q is true. Well, Now we need to ask what's the set of all states in which the logical formula Q is actually true, and X is the set of all states that we can want to go to as a winning condition. Angel would have won the game if only she would be here at the end. So what then is the set of all states in which Angel has a winning strategy to win the game of challenge into the region X? Well, first of all, Angel had better start in the region X, right? Because if, for example, Angel would start here, that would be very bad because tests never change anything, right? So she's not inside the region X and never will be, no matter how often she's trying to pass the test. Likewise, of course, out there would be very bad for Angel. Does she have a chance to win when she's here? No, she doesn't either. Not because she's outside the winning condition that she's trying to reach, but this time because she's failing the test that she's supposed to pass. In other words, the only case that works is when Angel starts in a state in here in this intersection, and that means, of course, precisely this intersection is the semantics of test games. Angel does have a winning strategy in the game where she's challenged to make Q true, to win into the winning condition where X is true, so make it to X. Whenever, well, first of all, she's already in X, and she's also in the set of all states where Q is true. So she passes the test and is already at the winning condition. She's in this intersection. These were all the atomic games. Now, of course, we'll have compound games to worry about. The first of these is the game of choice. Under what circumstance does Angel have a winning strategy to win in the game of choice between playing alpha and beta subgame? And where she wants to be at is the winning condition X. So she wants to reach one of the X states, and her choice, at least, whether she would like to play alpha or beta. That's the good thing. So let's look at this in pictures. This is the winning condition where Angel would have won the game. That's the winning region, so the set of all states where if Angel were to choose the alpha subgame, she would have a winning strategy to make it into X. And that's the set of all states where Angel would have a beta winning strategy to reach one of the states in which X is true. So where does Angel then have a winning strategy to win a game of choice between alpha and beta? Well, good news is Angel is still in charge of choosing her own choices, because alpha choice beta gives Angel the opportunity of choosing what she would like to do, whether she would like to play alpha or beta. Of course she's in charge, so if the game starts here, well, then Angel has a winning strategy in the game of choice. All she needs to do is, well, play alpha, somehow make it into X ultimately. If the game starts here, Angel also does have a winning strategy in the game of choice, alpha or choice beta, because all she needs to do is to decide that she wants to play the beta subgame and then follow whatever winning strategy it was that made her won in the beta subgame. What now, however, if Angel starts here? Well, then of course she also will win the game, because all she needs to do is decide whether she would like to play the alpha subgame or the beta subgame, which at this point doesn't matter that much. Nay, it doesn't. She can basically toss a coin at that point, or just choose arbitrarily, for example, left. And then she will have a winning strategy to make it into this region as well. In other words, the semantics says that the set of all states where Angel has a winning strategy in the game alpha choice beta is, of course, the union of the set of all states where Angel has a winning strategy in the alpha subgame to win into the region X, union the set of all states where Angel has a winning strategy in the beta subgame to win into X. It doesn't matter which of those regions Angel is, she's going to have a winning strategy either way. Of course, she won't have a winning strategy outside here, because, well, she never did have a winning strategy in alpha nor in beta, so if she's faced with a decision whether she would rather like to place alpha or beta, she has no choice to actually make it win. Now, for the sequential composition, how do we play a sequential game? Well, how would you do that? Angel still in the winning region for the sequential game, first alpha, then beta, she still wants to make it into the region X. How can we reduce this to questions about subgames? The two subgames we've got are alpha as well as beta. Now, if Angel would have a winning strategy in the beta subgame to make it into X, then, well, that gives us some set of states from which she will have such a winning strategy. So from all of those, there's some way of winning into this. Now, what does she do with the alpha subgame, though? Oh, of course. I see. Now we can ask, in what set of states does Angel have a winning strategy in the alpha subgame to make it into, what's the reason she wants to reach? Well, of course, there's this very region, the set of all states in which she will have a winning strategy in the second subgame. So that means this is the set of all states from which Angel in the alpha subgame will have a winning strategy to make it somewhere into this region, and then she will have a winning strategy in which she continues. In other words, the semantics of the sequential game is that Angel has a winning strategy in the sequential game, first playing alpha and then playing beta to make it into the set of all states where X is true, which is exactly the composition of the functions, which is the winning region in which, in the alpha subgame, Angel has a winning strategy to make it into the slightly more complicated region here, which is the region in which Angel has a winning strategy in the beta subgame to make it into X. So she has a way of winning into this region in which she will have a winning strategy to make it into her actual goal region. And that makes a lot of sense. The semantics of a sequential composition of games is precisely the composition of the games. Now, what about duality? And how do we define what the semantics is in which Angel has a winning strategy in the alpha dual game to reach into the region X? Ooh, that's difficult. So, what are the subgames that even exist for the alpha dual game? Well, the only subgame you could think of, because we don't know what alpha looks like, is of course the alpha subgame. So how can we express as a function of alpha what Angel has as a winning region? Well, she can basically ask herself, what are the set of all states in which she doesn't want to go to because she would have lost the game? That's the complement of X. X is where she would have won, so X complement, the other states, are the ones where she would have lost. She really doesn't want to go there. Now, what are the choices that Angel has in Alpha Dual? Well, these are the choices that Demon has in Alpha and vice versa. So what she can do is basically play from the perspective of the opponent and say, what's the set of all states in the alpha game where even if we are in X, we could still reach X complement? So that means here she's asking from the opponent's perspective in the alpha game instead of the alpha dual game, if her opponent, for whom she's pretending to play in the alpha subgame, has a winning strategy of reaching the region she doesn't want to go to, the complement of X, then these are all the states in which she's doomed, because the opponent, of course, will, in the dual game, precisely have the choices that she used to have in the alpha game. And that means the complement of that region, so the set of all states in which it is not the case that in the ordinary alpha subgame that would she have a way of running into the region that she doesn't want to go into, which means their opponent is going to take the choices that she doesn't want in the alpha dual game. And that's precisely the set of all states that is the winning region for the dual game. That was a very subtle case. Let me say it again. Angel wins in the dual game to achieve X exactly in the set of all states in which she doesn't, that's where the complement comes from, have a winning strategy in the ordinary hybrid game alpha, which she's pretend playing for her opponent to achieve the opposite, X complement. And that essentially means Angel is asking herself when simulating Demon's action in pretend play for alpha, but of course you'll have to remember that Demon's purpose isn't necessarily to make Angels happy, so she's asking herself in the ordinary game with the flipped roles alpha, where would her opponent like to go? He would like to go into the complement region where she would have won, and if he's able to do that, she's lost, but if he's not able to do that, so the complement, then she'll have won. These were all the cases, except the repetition. We'll see about that a little bit later on. These were all the cases for the question whether Angel has a winning strategy in a game, alpha, in this case alpha dual, to win into the several states where X is true. But of course, that only gives us a semantics for the alpha diamond P case. Remember what we said? We said the semantics of alpha diamond P is that it's true precisely in the set of all states where in the game alpha we can win into the set of all states where P holds true. And that has now been defined for all the cases the alpha could have, except the repetition that we'll see later on. But we still need to worry about what happens in the box modality, because remember, we used to say the set of all states where alpha box P is true is precisely the delta of alpha and the set of all states where P is true. That means the set of all states where Demon has a winning strategy when playing the hybrid game alpha to make it into the set of all states where P is true. So that needs an entirely new definition, of course. So when Demon is in charge and he's asking himself, how does he win in the game of assignment into the region where X is true? How does he know from which sort of states he has a winning strategy? So which sort of states is in exactly this winning region for Demon? There weren't any choices for Angel in the assignment game. There aren't any choices for Demon in the assignment game. There just are no choices whatever in the assignment game. It just is assigned deterministically. So, of course, also for Demon, that will be the exact same thing. The set of all states in which after you assign the value, so after you change the value of X in the state omega, to assume the value that it will have in a minute now, so the value of E in the original state omega, if that state is in the set of all states where a Demon would like to go, that means if we jump over and reach Demon's favorite target, then of course that's the set of all states in which Demon has a winning strategy, because it's not like anybody's got any choices in assignments. For a differential equation, it's like that. For a differential equation, if Demon's asking himself, what's the set of all states in which he has a winning strategy to play the differential equations game within the evolution domain constraint Q to reach the set of all states where X is true? Well, it's a matter of asking what solutions of differential equations look like. But the twist is that, well, Angel is still in charge of choosing the duration of the differential equation, and since Angel isn't necessarily helping Demon, the only set of states where Demon is sure to have a winning strategy, he really does, is the set of all states where each and every one of those solutions, no matter what the duration is, as long as it satisfies Q, will also remain in X, because otherwise Angel could leave that and announce that she's won and Demon lost. So that's precisely the set of all states where for all the solutions and all the durations of solutions, the initial state is in this winning region whenever all those final states for all of those solutions are in the winning condition X, so they're in the coral region. Because it's not Demon's choice, so he'll have to be prepared for whatever duration Angel chooses. And of course, we still have the exact same notion of what it means to solve a differential equation as we had already developed in the second chapter of the textbook. What happens for tests? If Demon is challenged and he's running the game test whether Q is true, when does he have a winning strategy to make it into the set of all states where X is true? Well, let's play through the cases again. Out there, Demon is in trouble because he's not in the region X. In here, Demon will have won the game because he is in the region X. And, well, what does a test do? Well, I guess it passes on that point, but never mind. What happens over here? Well, Demon's in the winning region. The test didn't pass. Whose fault is that if the test doesn't pass? It's Angel's test, remember? So it also ought to be Angel's responsibility for testing this thing. So either way, Demon will have won because he's in his favorite target region. It's not his fault if Angel's test doesn't work out. Come to think of it, what if Demon is indeed out there? Well, then even if he's not in his favorite winning condition X, he isn't at the goal where he would like to be, but still, wait a second. It was Angel's test. It was Angel's challenge that she's being challenged to make sure that Q is true. It isn't true, so it's Angel who lost. Prematurely, because of violating the rules of the game, but Demon doesn't mind. He'll claim the victory. So also down there, actual Demon already won. So well, is there any state at all where Demon won't win, but Angel's being challenged with the test Q? Well, yes, there is. In here, Demon's in trouble. Because Angel, because she's inside the set of all states where Q is true, very much will succeed and pass the test whether Q is true. So she played by the rules of the game, but Demon wasn't where he would like to be. In other words, the set of all states where Demon has a winning strategy to win Angel's test is whenever either Angel fails the test, so we're outside of the set of all states where Angel will have played by the rules, and then it doesn't matter whether we're in the region X or not. Or, well, we're inside that region, but at least we will make Demon win the game. Whether we're inside the several states where Angel has passed the test or whether we're outside, either way doesn't matter. Demon already won. What happens in the game of choice? When does Demon have a winning strategy in the game of choice between alpha and beta to make it into the winning conditions of the several states where X is true? Well, again, there's two subgames to worry about. There's the set of all states where Demon has a winning strategy in the alpha subgame to win into X, and the set of all states where Demon has a winning strategy in the beta subgame to win into X. Where does he then have a winning strategy in the alpha choice beta subgame to win into X? Well, let's see. If we start in here, Demon will win the game, right? Because it doesn't even matter whether alpha or beta is played. He's going to make it into X because there is such a winning strategy. What if we start down there? Well, what if we start there? Demon would have a winning strategy in the alpha subgame to win into X. So somewhere like so. But it's not like Angel will, if we're here, have to choose the subgame alpha. it's the game of choice, but it's still Angel's choice to make, not Demon's choice to make. He would very much like to play the alpha subgame here, but he has no say. It's Angel's determination. And Angel, if she's clever, is going to say, let's play the beta subgame here, in which case Demon doesn't know how to win. In other words, only the intersection of the two winning regions is the one where Demon actually has a winning strategy, because he doesn't call the game. Only if Demon has a winning strategy in the alpha subgame to win into X, and so intersection, he has a winning strategy in the beta subgame to win into X. Only then will he survive Angel's choice, because no matter which side she's choosing, Demon will be in X at the end anyhow. Good. So notice, it actually does make a big difference whether we're playing hybrid games from Angel's or from Demon's perspective. Come to think of it, we're also talking about Angel's or Demon's winning strategies. So no wonder that these are different. What now happens with a sequential composition game? What's the set of all states where Demon has a winning strategy in the first play alpha, then play beta game to win into the winning condition X, so to reach the set of states? Whose sequential composition is that? Is it Angel's or Demon's? Well, no. That question wasn't very meaningful, because of course a sequential composition just happens. Having played alpha, the play continues with playing beta, except when one of the players prematurely lost the game during alpha, but that's already handled somehow. So, in other words, of course, we will still ask, from which set of all states does Demon have a winning strategy to make it into X in the beta subgame? And then we will ask ourselves, what's the set of all states in which Demon has a winning strategy in the alpha subgame to win into that region we just described? So in other words, also for the winning strategy's existence of Demon is the sequential game merely such that the winning region for alpha semicolon beta is just the composition of the winning region functions. Compute where Demon will win in the inner subgame, and then compute where Demon will win in the outer subgame to make it into this region that we just talked about. Again, we're skipping repetition for a moment and look at the duality case. Again, this is going to be a bit surprising. Demon asks himself, where does Demon have a winning strategy in the game Alpha Duel to make it into the region X? Well, remember, Alpha Duel flips everything around, right? So the only subgame we have is the Alpha subgame, and Demon now needs to pretend play for Angel. So this region X is the set of all states where Demon would like to be. But that means the complement of X is the set of all states where Demon really wouldn't like to be, which means Angel might want to go there. So then he asks himself, the choices that he has in Alpha Duel are, of course, the choices that Angel has in Alpha, and vice versa. And that means this is the set of all states where, when flipping the perspective of the game, there would be a way for Demon to, if he's pretend playing for Angel's choices that she has an Alpha Duel, that Demon has a way of making it into the unfavorable region, the region where we're in the complement of X, so Demon would have lost. And that means if we're in the complement of that region, so the region where there isn't a winning strategy in the ordinary alpha game for Demon to make it into this region that he doesn't want to go into, then because we're actually playing the duel game, the Demon won't lose either, and that means it's the complement of that. That means Demon wins in the duel game to achieve X in exactly the set of all states in which he doesn't have a strategy, so it's the complement of that. In the ordinary game alpha, with everything flipped and pretend play to achieve the opposite, the thing he doesn't want. He doesn't want to be in the complement, and if in the ordinary game where everything's flipped compared to Alpha Duel, there is no way for him to win into the parts he doesn't want to go into, so win the complement of that, then he'll win the duel game. Summarizing what we've just seen elaborated with a lot of pictures and gradually developed, We've augmented the definition of the semantics of differential game logic with the winning region semantics for hybrid games, which is a denotational semantics. So for all hybrid games, are we saying for every winning condition X, so for all sets of states that we would like to get to, in this case Angel, what is the set of all states in which Angel will be able to, because she does have a winning strategy. And that's precisely this definition, which is actually very easy, come to think of it. But we're missing one case. We're missing the case of repetition, and really should be making up for that. But at least, take notice, we have now filled in these two cases, the winning region semantics for alpha diamond and alpha box, based on these two winning region or denotational semantics styles. They're just missing this repetition case. That shouldn't be so hard. Also, at this point, observe, because we'll need it later on, one useful observation, that monotonicity. It's easier to win into larger regions. So when we have a bigger winning condition Y that's containing X, then the set of all states in which Angel has a winning strategy to win into Y is also bigger than the set of all states in which Angel has a winning strategy to win into the smaller region X, and so it is for Demon. So if you take a slightly larger region that you would like to win into, then certainly all the winning strategies you already had in order to get into X, these ones, are still proper winning strategies to also win into Y, because you even win into X. But you might be able to add a few. You might be able to add extra states from which, now that it's a bit of a more liberal condition, just merely making it to Y as opposed to the smaller X, that might add a few cases where you can also win. And that's actually very easy to see from the semantics. Just very briefly, we'll see it in more detail in the next chapter, but basically, if we pass in a bigger region into the assignment case, then it's easier to satisfy that. We get more states out of this. If we declare a bigger region to be Angel's target, then there's more sets of states from which there is a solution of the differential equation to get there. If we make the target region a bit bigger for testing, well, then that gets a bit easier to satisfy this intersection. If we make the winning condition X a bit bigger in a game of choice, then this gets a bit bigger and that gets a bit bigger, and the union of two slightly bigger sets will only get bigger. For the sequential composition case, if X gets bigger, then the winning region for beta gets a bit bigger, which means this gets bigger, which means the winning region for alpha into that region gets a bit bigger. Oops, yeah, repetition, we still need to skip. And the duality as well. That's more subtle, but basically, if X gets a bit bigger, then X complement gets a bit smaller, then this set gets a bit smaller, then the complement of that set gets a bit bigger again. Never mind too much about this. Just walk away with the monotonicity principle in your head, because we'll need it just once before we carefully revisit it again in the next chapter. So all we need to now add is the understanding for the semantics of repetition. Remember, this is a slightly bit challenging, because in this very innocently looking game, do we actually have to pay attention to the filibuster scenario? If we keep on playing this game, then Angel would never like to stop, because Demon can always thwart all of her goals by playing the one side that Angel doesn't want, so she can repeat, and nobody would ever really win the game unless we remind ourselves that Angel can only choose the repetition option in the repetition game any arbitrary but still finite number of times. Ultimately, she'll have to stop. And only for that reason does the game have a true value, this formula, and Demon indeed wins and Angel loses the game. But we have to pay attention to this well-foundedness in the repetition somehow. Now, how do we define the winning region for repetition? So when Angel gets to decide how often she wants to repeat, how do you make it into the set of all states where X is true, because that's the winning condition that she would like to achieve? Well, Angel gets to decide the repetition, and well, what used to be the meaning of repetition in hybrid systems? Precisely. It was just the union over all powers of alpha. So alpha power 0, alpha power 1, alpha power 2, alpha power 3, and so on. So alpha, semicolon alpha, semicolon alpha, dot, 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 and so on. So I guess for similar reasons, that's what the semantics should look like. Just like in a hybrid system, the reachability relation for alpha star was the union of all natural numbers of the reachability relation of alpha power n, where alpha power n is just the n-fold sequential composition of alpha. And I guess for similar reasons, we should be defining the winning region where alpha star can be won by Angel into the region where x is true as the union of all natural numbers of the nth sequential composition to x. Well, that might make all the sense in the world, but let's look at it, right? In the filibuster game, for example, right, we can stop the game or repeat, and then Demon can choose to play 0 or 1, and then Angel can again inspect and stop or repeat, and stop or repeat, and stop or repeat. But that was a very interactive gameplay, whereas on this side here, what happens is basically it's correctly the union expressing the fact that Angel gets to decide how often she wants to repeat 0 times, or 1 times, or 2 times, or 3 times, or 4 times. But when she said that, Demon knows, and she can't change her mind about it. So, for example, if she decides to play 2 times, well, then Demon precisely knows that he'll have to play 2 times, and then Angel has promised to already stop. If she decides 4 times, well, then Demon also still knows that, right? He now knows that Angel is apparently playing alpha power 4, so he will have to be prepared to play exactly 4 rounds of the game. And all of a sudden, this advanced notice semantics, where Angel plays repetitions by announcing ahead of time exactly how often she will repeat the repetition, are much harder for Angel to win, because Demon can now make sure essentially that, well, Angel doesn't win in exactly 4 rounds. She might need 1 more round, or maybe she would have won a previous round. And here's one of those examples you can think through to notice why there really is a difference between the semantics you want, the interactive gameplay, stop-repeat gameplay, and the advanced notice gameplay. So in other words, super convincing, but unfortunately dead wrong, because if you play the alpha star subgame by instead choosing a number and then playing the alpha power n subgame, the opponent can very much read the n. You need something else. It's too hard to predict exactly how many iterations the game will play. Notice something very useful, namely, whenever you have a set that's in the winning region for repetition, so the several states where there is a winning strategy in the repetition to reach several states where x is true, well then if you play 1 more time, it should also be in this several states where there is a winning strategy in the game of repetition to reach into x. So if you ask yourself, playing 1 more round, can I win into y, then all the sets of states that we get here should already be included there, because, well, no matter how many rounds we needed to win y, this is just 1 more round away. In other words, if we have some set of states that's inside the winning region for repetition, then all of its successors, in the sense of all of the sets of states from which there is a winning strategy to make it into this region, are already included in this. So if we ask about the opposite, then that set is actually empty. There's nothing extra that isn't already here. That makes sense. That's a +1 argument, basically. You can always play 1 more round. Let's make use of that and define a slightly different operator. An operator defined like so, that now is the n-fold composition, essentially, of the winning regions, which says 1 more round, and 1 more round, and 1 more round. How do you do that? Well, we say you can win the game in 0 rounds into the winning region x. Well, precisely if you start in x, because 0 rounds don't do a whole lot to you. You can win in one more round than kappa whenever, well, you started where you were, because sure, you could stop. Or you can play one more round into the set of all states where apparently kappa rounds have been enough. So playing kappa plus 1 rounds of the hybrid game alpha will make you win into X whenever you already did, or whenever one more round will get you into the winning sets where kappa rounds would suffice. Okay, that means, in 0 rounds, I guess you would have only won when you already start in X. In one more round, you would have won here because, well, you can play your way down there. In one more round, you would have won because you can play your way into this, from which apparently you have a way of playing further into X. And one more round, and so on. So the union over all of those. Is that actually markedly different than the alpha power n, which was the sequential composition of alpha n times that led to the advanced notice semantics? Yes, it is, because while there still is an n, it's at least outside the game. It's not syntactically part of the game, so Daemon won't know how often you will nest this winning iteration argument. You can't predict that. So that's what makes this semantics a lot more helpful. This is the omega semantics. Now let's look at an example. Here's a simple example where we're asking ourselves, does Angel have a winning strategy in a game of repetition to make it into a state where X is between 0 and 1, exclusive from the top end, where she's in charge of repetition. She can choose how often. She can choose left or right. If she's choosing the left subgame, then the value of X is reset to 1, and then control is given to the opponent Daemon, who's following the differential equation x prime equals 1 for any arbitrary amount of time. If Angel's choosing the right subgame, then we merely subtract 1 from X. Okay, let's compute the set of all states where there is a winning strategy for this according to the semantics. Well, where do we win in 0 rounds? Of course, in 0 rounds, we only win if we already start between 0 and 1. If we do one more round like this, well, then we basically say, from where can we get into the interval 0 to 1 by assigning 1 and then following the differential equation x prime equals 1 under Daemon's control for an arbitrary amount of time? Well, that never has to get us into 0, 1, right? So that doesn't actually help. But that choice, it does help, because by subtracting 1, it's easier to get into the interval from 0 to 1 just from the interval from 1 to 2. And because we still have the old interval from 0 to 1 around, now we can win from 0 to 2. Let's do that again. Again, the left-hand side isn't very helpful because, this differential equation under Daemon's control could increase the value of x arbitrarily, but still, by subtracting 1, it's now 1 round closer to this. In other words, n iterations and nestings of this winning region construction here, 1 iteration at a time, will enable us to win into 0, 1, precisely from the several states between 0 and n. Cool. But where do we win the repetition? Oh yeah, I remember. By unioning over all natural numbers. So let's union over all natural numbers of these winning regions. The union over all natural numbers of the intervals from 0 to n are precisely, that's all the non-negative real numbers. That's all the real numbers between 0 and infinity. That's good. Or is it? Well, now we've computed, according to this omega semantics, that this game can be won precisely from all the non-negative real numbers. But hold on a second. Can you win it under other circumstances as well? What if we were to start with -5? -5, which is markedly outside this, would, well, play the left-hand side, which will increase the value quite arbitrarily. But then all that Angel needs to do is just decrease sufficiently often until she's between 0 and 1 again. That sounds like a perfectly legitimate winning strategy. How could we possibly miss it? In fact, now that we've concluded that, union of all natural numbers of the winning region construction iteration will give us all the numbers from 0 to infinity, what happens if we simply do this thing again? We compute the successor, so where can we win into the region X that we already have, right? Or in one round, can we win into the region 0 to infinity? When we ask ourselves, how can we win into the region from 0 to infinity in this game? Well, the right action doesn't help a lot because it already includes all the numbers from 0 to infinity. If we subtract 1, we're still in this region. But on the left-hand side, by resetting x to 1 and then following the x prime equals 1 under Demon's control for an arbitrary amount of time will certainly get us somewhere in this region because we started 1 and then keep on increasing. That might lead us to a billion, gazillion, trillion, but it'll still lead us into this set of states. In other words, by playing one more round into the infinity plus 1, or more precisely omega plus 1 iteration of the winning region construction, we suddenly find out that the set of all states we can win from is all the real numbers. And last time I checked, there's a big difference between all the real numbers and just the non-negative real numbers. So that's shocking. How could it happen that after we've made infinite amounts of works of computing winning regions succession one step at a time, we still find a bit more by doing this once more? So we've unioned all of those, 1 times and 2 times and 3 times and 4 times and 769 times, 1 billion gazillion trillion times. We've done all of this like infinitely often, once for every natural number. And if we then do it once more, we find more winning states from which there is a winning strategy. That's peculiar. In fact, the reason why we dismiss the omega semantics for repetition is because it's missing out on perfectly legitimate winning strategies, and that wouldn't be any good. And in fact, it turns out that this happens in the complexities of hybrid games shockingly often and far. That there's games you can win 1 more round, 2 more rounds, 7 million, gazillion, trillion, billion more rounds. Having done so infinitely often, once for every natural number at the ordinal omega, we found out that we're not quite done yet, but we need to do it one more time. After having done an infinite amount of work, we need to do one more round of work, as we just did in the previous example. But there's also cases where we're not done yet. We need to do one more round of winning region computation, and one more round, and one more round. In cases where we have to do the whole thing infinitely often, so now we're at the ordinal omega times 2, having done an infinite amount of work twice in succession, which is kind of a bother. But there's also cases where we're not done yet. We need to do this once again, and the whole thing infinitely often, and the whole succession of infinitely many steps infinitely often. So go to infinitely many steps and infinitely many steps and infinitely many steps. The whole thing once per natural number, which takes us to the ordinal omega square. Right, having done infinite amount of work infinitely often. But there's also hybrid games in which we're still not done, but we have to do one more round, and and have to do the whole thing maybe still infinitely often then, and the whole thing infinitely often until we're finally at omega cube. And in fact, how come to speak of it, the entire construction, there's cases where we have to do infinitely many of those winning region constructions infinitely often, in which case we're at infinity power infinity, or more technically precise, omega power omega. So repeat the entire infinite set of winning region constructions infinitely often. And in fact, honestly, there's cases where hybrid games are even more complicated than that. They go up to the Church-Kleene ordinal. So in other words, hybrid games are quite challenging, because if you ask yourselves, when do those winning region constructions ever stop, we'll have to do more than an infinite amount of work, and I'm perfectly happy to do an infinite amount of work, but not more than that. And hybrid games in this style that we just saw would require a whole lot of infinitely more work than infinitely more. Brief expedition into ordinal arithmetic. These are basically, well, generalizations of natural number orderings, where if we have one of those ordinals, we can always add 0 to it, and we get the same number back. We can add a successor of an ordinal to it, and of course get the successor of whatever the addition of the two got. or we can add one of those limit ordinals, these infinities like omega and omega square. And we just get the least upper bound or supremum of all the additions of all the smaller ordinals. And we can multiply. For example, multiplying any ordinal with 0 will give us 0. Multiplying an ordinal with a successor of an ordinal will give us, well, the iota addition to the multiplication of the smaller ones, just like you would do natural numbers. The multiplication with a limit ordinal, such as the omega, is just the least upper bound or supremum of all the multiplications with all the smaller ordinals. The exponentiation this way, and so on. And you find out rather surprising things because of this non-commutative definition of multiplication, that 2 times omega is very well the same as 4 times omega, because they're just both omega. But on the other side, omega times 2 is much smaller than omega times 4, because by the time we went to omega times 2, there's still quite a lot of distance to go all the way to omega times 4, namely infinitely many, and yet again infinitely many ones per natural number. But never you mind the ordinals. We can define a winning region like that. We can define, if we just keep on completing this process, we keep on unioning an infinite number of all of those, so the supremum of ordinals, then we can define the winning region semantics like that, starting in X, doing one more round of alpha, doing one more round of alpha, doing the whole thing, and again, doing that infinitely often. And having done so, we do it one more time, do it infinitely often. Having done so, we do it one more time, and do it infinitely often, and so on until this process stops, which it ultimately actually will. So as long as you remember that there's like infinitely many dots in between here actually, and of every color you could possibly think of, then this will give you a legitimate semantics, in inflationary semantics for repetitions in hybrid games. It might also have gotten you a headache, because this semantics, while being perfectly legitimate, also requires transfinite amounts of patience, more than infinite patience. For that reason, we're moving away from this explicit construction to an implicit definition, where we find the bon mot of Bertrand Russell, who essentially said that the advantages of implicit definition over construction are roughly those of theft over honest toil. Now, I'm a big believer in honest toil, but I also do like implicit characterizations of properties. Let's use them to simplify our constructions. And the way to do so is to remind ourselves about the +1 argument. Whenever we have a set that's in the winning region of repetition, then if we ask ourselves where could we win from if we were willing to do one more round, is also already in the winning region of repetition. Because, come on, it's just one more round away from Y. Let's exploit that. If we have a set, for example, Z, or was that, that is the winning region of repetition itself for reaching the winning condition X, well then that set also should satisfy the +1 argument. So if we ask ourselves where do we go for winning one more round, by this same +1 argument is already contained in there, but hey, that was actually the set we called Z. That means the winning region of repetition itself doesn't change. If we ask it, could we go anywhere else if we were willing to play one more round? Sure thing. The winning region of repetition shouldn't get any bigger if we ask, can we play one more time? Like my child would all the time. Now, with this observation, we basically find out that the right answer, the winning region of repetition, has a successor in this winning region iteration that's already contained in itself. Now, if we take that as a beginning of an implicit definition, we can ask ourselves, well, which set of the ones that satisfy this inclusion principle is the one we're looking for? Are there multiple such sets, or is this the only set of states? If so, that would be an awesome definition. But hold on a second, does such a set of all states even exist that satisfies this condition? The question whether playing one more round is already included? Well, it does exist, right? The empty set does it. Now, hold on a moment. Now we're saying the set of all states from which Angel has a winning strategy in the game alpha to win into the empty set of states. That sounds empty, but she might still win, even if it's impossible to satisfy the winning condition, because it's the empty set of states, if only she can trick Demon into losing. Yes, indeed, right? If there's dual tests, for example, then even if Angel doesn't have a single state in which she will win, she will still win by fooling Demon into prematurely violating the rules of the game. So that means, indeed, in that case, it's the complement of the tests that Demon has to pass in this dual test, and that's not contained in the empty set. But if we make up for that somehow, and we add in the negation of Q, then we would find one of those winning regions. And that sounds like one actually exists, but it's too small, right? Because even this doesn't take into account what the actual goal of Angel is. She wants to win into X, and so X really should be part of the set Z as well, because Angel may very well decide not to even repeat at all. And that means the actual characterization that we have is that this set that we're looking for should not change anymore, should already be included in the set of all states from which we can win into Z, but it should also very well include X itself, the target region, because repeating 0 times should always be an option. And that condition here is now what's called a prefix point. It's a set of all states Z that's satisfying the condition that, first of all, it includes X, but then also if we ask ourselves, what's the set of all states in which playing one more round of alpha will take us into Z? That set of all states is already included in Z. It could shrink, but it shouldn't get more. And that is certainly true for the winning region itself, as we just saw. Basically, that means if we add one more round, we shouldn't add actually anything extra, and we should include X itself. Now again, which of those sets Z that satisfy this prefix condition is the right one, or the multiple ones? Does it even exist at all? Existence is now clear, because certainly the set of all states satisfies this, because no matter what pile of states we've got on the left-hand side, they're certainly contained in the set of all states. But that can't be right, right? We cannot possibly define the winning region for repetition to be, no matter what the game was, no matter what the condition was, to always say you always win, Angel. That would be making life a little bit too easy and too boring for Angel. So existence is not the issue, but which one is it then, right? Which one do we choose? Apparently there could be multiple of those prefix points. Maybe. Suppose there are two. Suppose we've got a set Y that's satisfying this prefix point condition and a set Z that's satisfying this prefix point condition. Then what else do we know satisfies the prefix point condition? Exactly, their intersection does. The intersection of Y with Z also is a prefix point, and smaller, or maybe just as big, but at least not bigger than each of them individually. In other words, these prefix points are closed under intersection. And why is that? Well, because Y intersects Z, that's the condition it needs to satisfy. And why does it do that? Remember the monotonicity principle. This set is a bit smaller than that, so the winning region of that is also a bit smaller than the winning region of that, in the sense of subset inclusion or equality. And that's still true even if we union X into this, but also Y intersect Z is contained in Z, right? So it also, this winning region is a bit smaller than that winning region. Also stays the case if we are unioning in X, and that means this inclusion is actually true, but by that argument, X union this is contained in Y, but X union that is contained in Z. So the whole thing is certainly contained in Y intersect Z because it's contained in both, and that's precisely the prefix point condition. And in fact, it didn't matter we worked only with two of those prefix points are closed under any arbitrary family of intersections of them. Intersection of any family of prefix points is still a prefix point. It exists because, well, the set of all states satisfies that, and that means we can now keep on asking, do we find a smaller one, and the smaller one, and the smaller one, and the smaller one, until we find precisely that. The least of those, I guess, is what we're going for, because the semantics of repetition ought to be well-founded. We ought to ultimately call it a day. Angel can decide to stop or go any number of times, but she ultimately has to actually to settle on stopping, not going on forever. And that now gives us a very well-defined meaning of what it means for repetitions to ultimately stop. Here's the construction for that. Apparently the set itself, the winning region of repetition, satisfies this prefix point condition by what we just argued about, because it is the intersection of a lot of those solutions, and because, well, it's the intersection of a lot of sets that satisfy the prefix point condition, it itself satisfies the prefix point condition. If we call that set Z on the left-hand side, and we ask by the +1 argument, what happens if we, again, do one more round of the repetition, then that's by monotonicity contained in running one more round of the winning region of repetition, because, well, Z is contained in that, so the winning region mapped over both of them also is an inclusion. That inclusion continues to be the case if we union X on both sides, but if we union X on both sides, then what we found on the right-hand side is precisely the set Z that we started out with. And that now means that X union the winning region into Z is contained in Z. That means because this winning region of the set of all states of repetition into X has to be contained in Z itself, because, hey, since this apparently is satisfying this prefix point condition itself, but that was the least fixed point, it must be a subset of this. And that means this is included in that, but from that we derive that they're actually equal, which means the set of all states, which is the winning region of repetition, we have defined with an inclusion here. We could have equivalently defined it with an equality here. The set of all states that's the winning region of repetition is not just the least prefix point, it's also the least fixed point. At least, remember, that's the intersection of all the states, sets of states, Z, such that they satisfy the fixed point or prefix point condition. That X union, where do I get to by playing one more round and winning into Z, is already included in Z, or rather in this particular case is even equal to Z. And by the seminal result of Denotational, it is actually possible to prove that these least fixed points are equal to what we used to define with the inflationary semantics as the union, constructing it up explicitly from the bottom of, unioning one more round and one more round and one more round, just, infinitely often, and then some, infinitely often again, and infinitely often, and the whole thing infinitely often. This fixed point characterization is more intuitive to work with, because it gives an implicit characterization as opposed to an explicit construction of the set. Let's summarize what we've seen. We've now developed the, admittedly somewhat subtle, semantics of hybrid games, but we end up actually walking away with an easy construction for it. Remember, the winning region of repetition could either be defined as the inflationary construction or, by Denotational, as the least fixed point condition, and we do settle as a least fixed point condition as sort of the official choice, but remember that both of them would have been possible. What's the semantics now? The semantics is actually a pretty easy function. The semantics of differential game logic formulas is just as it already was in differential Hamming logic, with the modification being that the set of all states where Angel has a winning strategy in the hybrid game alpha to reach one of the states where P is true is the winning region of where Angel does have a winning strategy in the alpha subgame defined up here, to win into the set of all states where the post condition is true, which is already defined recursively, And likewise, there's a corresponding definition for alpha box P, so the set of all states where daemon has a winning strategy to win in the hybrid game alpha to make it into P, which is a corresponding construction. And most of those cases are actually pretty easy. For example, having winning strategy into X is long an assignment. It's just, well, what are the states from which the assignment will land us into the goal region X? There were no choices. For a differential equation, it's more interesting. Angel does have a winning strategy in the differential equation x prime equals f of x to win into X. From all the initial states from which there is a solution for some duration, such that at the end we are in X, there is a winning strategy for Angel in the challenge game, testing whether Q is true to win into X whenever she's already in X and she also meets the requirements of the test. Angel has a winning strategy in the game of choice to win into X whenever she has a winning strategy in the left subgame to win into X, or she has a winning strategy in the right subgame to win into X. Angel has a winning strategy in the sequential composition game to win into X whenever it's the composition. So whenever there's a winning strategy in the alpha game to make it to a state from which there is a winning strategy in the beta game to make it into X. The winning region of repetition, that was more complicated, was the one where we ultimately set it for the least fixed point condition. So the set of all states where Angel has a winning strategy in the game of repetition to make it into X is the least, so it's the intersection of all the fixed point or prefix points, Z, where they do contain the goal region X, but they also already contain all the states that we can go to by playing alpha one more round. They're all already included, and out of all the sets Z that satisfy this prefix point condition is the winning region of repetition the smallest one. It's the least fixed point of that. For the duality, we say that Angel has a winning strategy in the dual game to make it into X. Whenever in pretend play, there is no winning strategy in the ordinary game alpha to reach the opposite X complement. And whenever that's not the case, whenever she's in the complement of that set, she has a winning strategy in the dual game. We've now seen differential game logic, which is a combination of game logic with hybrid games, or equivalently of differential dynamic logic with a duality operator. And we've now developed an actual semantics for differential game logic, and we've experienced how, on the one hand, we walked away with very simple compositional denotational semantics for it, but even if the meaning is a simple function of the meaning of its pieces, the potential outlier was the repetition, which, due to its pretty subtle higher ordinal iteration construction, was surprisingly complicated. Much better did it become when we said, never mind how to construct it, the meaning of repetition is a least fixed point. And indeed, that's what we did observe, that hybrid systems are a lot easier, because for hybrid systems, after an infinite amount of work, meaning at the closure ordinal omega, we're actually done. But in hybrid games, these constructions might go on and on and on and on and on and on and on, even to things like infinity power infinity, or more technically precise, omega power omega. Now, however, that we do have a solid understanding of differential game logic and hybrid games and their semantics, we're now well prepared to look in the next chapter an axiomatic development for them and figured out not just that it is now well defined who of the players wins the game, but also to find out how to win the game and how to prove a hybrid